All right, in our first example, we're going to take a look at a horizontal translation of a linear function. Horizontal translations is just going to take our linear function, it's going to shift it to the left or to the right, depending on the function. So in part A, how does adding a constant k to the input of a linear function affect its graph? So let's remember the input, those are the x values of our linear function. So here's just our regular linear function, f of x equals 2x minus 4. Now if we add in a constant value to the input, it would look like this. Here's our input x, and now we're adding in a 5. So how does adding in the 5 affect your graph? So we're going to kind of discover how it affects the graph by filling in table of values here. I'll try to do this quickly. Table of values, these are all of our x's. If we plug them into our function, 2 times each x minus 4, we're going to get back the value of the function. Those will be the y values. So what is 2 times negative 4 minus 4? What is 2 times negative 3 minus 4? Was 2 times negative 2 minus 4? So I'm just going to fill this in for you guys. We don't need to do that math together. So you can fill this in with me. If you plug in a negative 4 for the x, you're going to get a negative 12. If you plug in a negative 3, you'll get a negative 10. A negative 2 will give you a negative 8. If you plug in a 0, you get a negative 4. If you plug in a 1, you get a negative 2. If you plug in a 2, you get a 0. And if you plug in a 3, you get a 2. So again, all we did, maybe I'll just highlight this 3 down here. 2 times our x, well, if our x is 3, 2 times 3 is 6. 6 minus 4 results in that 2. Okay, so now what if we add 5 to our input? So instead of a negative 4, what is negative 4 plus 5? So negative 4 plus 5 is a positive 1. So now let's evaluate the function when x is a positive 1. So we would do, I'll just show this one on the first one, we would do, all right, 2 times our new x is a 1 minus 4. And 2 times 1 is 2. 2 minus 4 is negative 2. So I could have plugged in the negative 4 right here. Negative 4 plus 5 is 1. And then it would get us to right here, 2 times 1 minus 4. So we're just going through and recognizing how your input changes if you're adding 5 to it. So if you add 5 to a negative 3, now our input is 2. If we add 5 to a negative 2, our input is 3. If we add if we add 5 to our input of 0, we have 5. And then we'll keep going, 6, 7, 8. So these are the new input values when we add 5 to our x. So if we do 2 times 2 minus 4, 2 times 2 is 4, 4 minus 4 is 0. So filling all that in, let's just assume we know how to do that math. We're going to get a 2, a 6, then an 8, a 10, and a 12. So our next step is to graph the two functions to see, what kind of change. How did adding a constant of 5 to our input change? So our first ordered pairs are going to be these x's with these y's. Those are the outputs when we put in these x's. So negative 4, negative 12, let's see how graph goes to 1, 2, 3, 4, 5, 6. So we're not going to be able to fit everything on here. A negative 2 and negative 8 won't fit, but I'm going to fit 0, negative 4. So I'll plot that point. 0, negative 4. 1, negative 2 we can fit on. 2, 0. And 3, 2. And I mean, if we look at our function, 2x minus 4, the y-intercept is negative 4, which we have right here, and the slope is 2, so up 2 over 1, up 2 over 1, up 2 over 1. So we actually could just get the rest of those points because we know how to graph this, right? All right, so there is our first function, f of x. I'll go ahead and label that's our f of x function. Now the second one, when we graph this, our input is still the negative 4, but when we added 5 to it, now it was negative 4 plus 5, which is 1. So we did all this math, but we're still going to plot this x with this y. So -4, comma, -2. That will fit on the graph. -4, -2 is right here. Then we're going to plot -3, 0, -2, 2, 0, 6, no, oh yeah, 0, 6. So we're up here, and I can see that's all in a straight line. So if I fill in kind of some missing points, here's our g of x function. So just a couple things to notice is that our original function, f of x, is right here. G of x has the same slope, and I can see the slope here is 2. Here's the slope of 2 in the g of x function. It's kind of out in front of our x when we added something to the input. And then how did this change? So what we notice is the same line, but this line looks like it went 1, 2, 3, 4, 5 units to the left. 5 units to the left. Across the whole thing, we went 5 units to the left. So how did adding a constant k to the input of the function, or not how did, we'll just answer the question. Adding a constant k to the input of the function translates the graph horizontally. So let's throw in that word horizontal because this is a horizontal translation. Horizontally by k units. So if you add something to the input, your x, now remember x's are your horizontal values on a graph. It is going to affect your graph. It's going to move it 5 units. Now here is something that not all teachers say, but this is my way of helping you guys remember this. I call this the tricky x. And I used to play the song Tricky by Run DMC when I wanted to really, like, hey, students, remember the tricky x, tricky x, tricky x. What I think is tricky is this says x plus 5. So I would say, oh, I'm going to do a horizontal translation because I'm affecting the x's. But this plus 5 makes me want to go to the right 5 units. But the x is tricky. So we always shift in the opposite direction of what it looks like. It looks like a shift of 5 in the positive direction, but x is tricky, so we're going to go to the left 5 units. So you'll hear me reference that tricky x every time we talk about horizontal translations. All right, so let's just follow up, make sure we got this. Let f of x equal 3x plus 7. How does the graph of g of x equals 3 times x plus 9.5 plus 7 compare with the graph? So I'm not going to go through that whole graphing again. That was just for us to discover, oh, if I change something, if I add something to the input, if we're changing our x's, adding or subtracting something to the x's, it will be a horizontal translation. And we just talked about the tricky x, right? So it looks like I'm adding a 9.5. So that is going to be a horizontal translation to the left 5 units. Not 5. That was our last example. This one would be 9.5. So we're going to shift to the left 5 units. Another word for shift is horizontal translation. You do want to say which direction you are shifting horizontally. This one would be to the left because of that tricky x right there.